Our guest today, Alexander Irpan from Google DeepMind, will share what is happening today in robotics, how far we are from having autonomous robots navigating in our homes, and how large language models impact the development of robotics.
Promise or high-level goal of robot learning is to try to replace more of these stages with end-to-end neural nets that are trained from data in some way. In some sense, it's like, why should this like do things better? But I think empirically, this is based on observing progress in other subfields of machine learning and AI, where these sort of like end-to-end models that were data-driven have ended up achieving like the like best like general performance out of any other like prior more hand engineered method that we've seen so far. So I think this is sort of like the central like thrust or core belief in the robot learning like field, that data driven methods are the most promising ways to capture the long tail of outcomes, even if there's like a lot of challenges involved in capturing that long tail. So to briefly like talk about sort of my history with this, there's this paper I worked on in 2018 called QTOP Scalable Deep Reinforcement Learning for Vision-Based Robotic Manipulation. We submitted it to a conference on robot learning that year where it won a Best Systems Paper award. And very briefly, I don't want to get too into the details of how this worked, but it was one of the first like really big scale reinforcement learning systems that we got to run on a real robot. So we had this large, we called it the arm firm at the time. It was around like 7 robot arms, which were continually practicing trying to pick up objects out of a bin. So through this, we got like several like thousands of hours of robot data. There were around like 600,000 like robot graphs from the end. And then we ran an off-policy reinforcement learning algorithm based on Q-learning on those episodes to try to teach the robot how to grasp objects. By the end of that project, we got up to around a 95% grasp success rate. And interestingly, what we found is that the robot had learned some strategies which he didn't deliberately teach it to do. So in these GIFs here, we've given the robot this sort of arrangement of wooden blocks where it's a little tricky to pick up any object individually. And what we found is that the robot learns to sort of like poke down into the series of blocks, move things around until one of the blocks eventually becomes singulated and separated out from the rest. And once this happens, then the robot will like grasp and pick it up. And we found this really exciting because it was something that like naturally arose out of trying to make grasp successes be more likely. And it sort of indicated a little bit of notion of like longer term like planning or thinking like a few steps ahead in terms of what actions to take in the environment. Now, this did have a bunch of limitations. I think the big one is that it relied a lot on us having like an easy way to reset like putting objects in the bin. And we were also only really focusing on this single like bin picking task. But this was like one of the like first things that really made me believe that these sort of data-driven methods could like really go like further in robotics and if we kept pushing on them. So I've talked a little bit about like why these robot learning models have been hard, and I want to like take some time to like try to explain this in a bit more detail. So I think that the things that make robotics special is partly this notion of agency. So I know that in the more like LLM style fields, there is a lot of like interest in these notion of like large language model driven agents. Um, and I think that these are sort of like, they're like nice things to have with language models, but you don't necessarily have to make like a language model agent right now. If you're doing things in robotics, you don't really have the same luxury. Like the robot is an agent in the environment, and you just have to make this work. And I think that there are a lot of like fundamental challenges within getting agents to work that make the problem like quite interesting to me. But the fact that it's just an agent is not like the reason that I think robotics can end up being a challenging domain. Because when you think about things like game AIs that play like tic-tac-toe or Go, or even like you can sometimes cast like chat assistant things as like the environment is like the series of text you've like given so far. And these are still things which you can describe as agents, but I think the thing that they're missing that robotics has is this notion of embodiment. So in robotics, your agents exist in the physical world, and this creates a whole bunch of downstream problems. These are like important problems if you care about making models that actually like I guess one way to put it is like actually move like atoms in the world rather than like moving bits. Like if you want to actually like affect like physical change, you need to do things in the physical world. But this does create a bunch of like challenges. So I think one of them is this challenge of like data and complexity. So this diagram up in the top right is from this idea called like the coastline paradox, and it's this idea that like if you are say trying to measure the length of the coastline of Britain, at some point you decide like how long is like the most like granular measurement you're going to do here, and maybe you're looking at things at the level of like kilometers, and then you could zoom in at the level of like meters, and then at the level of like centimeters, and keep going further and further in. And the more closely you look at things, the more complicated this coastline becomes, and the harder it is to like really like define how long is the coastline of Britain. So this is a thing that sort of came up in like more of like a math setting, but I think it ends up like echoing in a lot of like robotics projects I've worked on over the years, that there's sort of this like almost fractal like complexity to reality. And when we try to get computers to do things in reality, at some point we have to like come up with some abstraction between that reality and like what the computer thinks is actually going on in the real world. And like because of this, there's always like a little bit of like disconnect in terms of like whether you are rounding off too much complexity from reality to actually like solve the problem correctly or not. I think that one of the other like related ideas in this space is like this notion of Moravec's paradox, which is uh, I think this is also from the 1980s. I might be forgetting the timing exactly, but very briefly, the way to describe it is that empirically for computers, trying to teach them to do reasoning seems to be easier than teaching them to do like walking and hand-eye coordination. Somehow, like a lot of these like basic things that we humans find easy for just like moving around are actually like really challenging to teach like a computer that's been embedded in a robot. I think that this has become especially true over time as more of the AI subfield has oriented itself towards large language models. And part of the reason that's the case is that these large language models are primarily trained on text from the internet. And I think that in practice, people on the internet like writing about like challenging things. Like they write about like, how do I like play this game of chess? How do I solve these math problems? How would I like do this like random like physics word problem I've gotten and so on. But there's not really like a same sort of like level of text of like, how do I like move the muscles in my finger to like move around? This is like maybe like the people who are like super into like biology will do this, but it's really not as common. And because we find these things so easy, we don't write about them. So then the models don't learn about them. And then like empirically, what this has turned into is that if you try to like directly connect large language models to like a robot, they will tell you that the robot should go to the fridge and should go to like the kitchen and pick up things there, but it won't have any idea of how to actually move like the motors in the robot to get there. And that's sort of like the actual like important bottleneck for getting robots to do things. So just in general, robotics friendly data in particular is like pretty sparse in the world. And there's just always a struggle in trying to get more of it that is useful and trying to use the data that we do have more efficiently. So uh, I think one of the very like common like replies I've gotten when I've discussed this with other people is how about simulation? So we've spent a lot of time working on like physics simulators that we use for like a variety of things. And intuitively, maybe we don't have a lot of data for robots moving around in the real world, but maybe we could generate a bunch more if we just simulate this robot in a physics simulator and run it out there. These have a very long history of use in robotics and just engineering disciplines in general. They are like very helpful for development, but there are some challenges in using them in more of like a data-driven setting, because in some sense, your simulation data is related, but it's not like exactly the same as the real like problem you care about. So this sort of echoes the like old adage that all models are wrong, but some models are useful. So really the question is, how wrong can a simulator be but still be useful? So there's another older project I worked on, which we at the time called like using simulation and domain adaptation to improve efficiency of deep robotic grasping. This was from around like 2017 or so. And the goal in this project was that we were trying to improve the efficiency of the real data we were using. So earlier I talked a little bit about this ARM farm that we used to do this grasp picking. Here's a video of that farm now. And at this point, we had already shown that by doing a bunch of like practice like grasp attempts, we could train robots to learn to pick up objects at a pretty high success rate. But we wanted to reduce the amount of real world data we needed, because collecting the amount of real data we needed was an order of like several months of data collection. So we implemented this setup in simulation. We ran our simulations on like the Google Compute clusters, which meant we could run a bunch of them in parallel, like several thousands of them. We had thousands of simulated robots picking up all sorts of randomly procedurally generated objects. And we were getting like millions of grasps in a series of like hours instead of days. And then we tried training a model on the grasps that were collected in simulation, and then took that model and just directly ran it in the real world with no extra like experience from the real world. We didn't expect this to work, and it didn't work. So this model that was succeeding maybe 90% of the time in simulation was only succeeding around 20% of the time on the real robot. So what we ended up doing is we used what was in the fashion at the time, which was generative adversarial networks. This was before diffusion image generation really like took off as a good like image editing paradigm. But we trained a model to take images from our simulator and try to convert them to look like more realistic ones. So in this image here, the left column is like the original images from our simulator. The right column is example camera images from our real environment. And this middle column is the output of the generative adversarial network, which was conditioned on images from the left column and told to generate images that look like the right column. If you look, it's not like exactly correct. There are some like artifacts around like these wires aren't really drawn in the correct positions. If you look closely at like some of the objects here, the way in which they're like textured and like leaning against like the side of the bin is like also a little bit wrong. But it turned out that this was like close enough. This was close enough that we could get some like learning improvements from this. And in all, in this project, we showed that we could reduce the amount of real world data we were using by like 50 times, and we would match the same performance as our model that was trained only on real data. So I think it was on the order of like 600,000 grasps, reduced it down to like around like 10 to like 15,000, if I remember correctly, and combined that with all of our simulated data that had been recolored in this way and retextured in this way, and it would reproduce the same performance. So this was like the state of things in like 2017. And well, now it's 2024. And now we have much better video generation models. So like, you know, here's like one of the ones from Sora that OpenAI released a few months back. I think that part of the reason that then we haven't like seen this become the super dominant paradigm right now is that a lot of video generation is focusing on making things that like look beautiful, or like making like the gross visuals look correct. This seems to like in practice be the kind of videos that you get out when you end up training like diffusion style video generator models right now. And just going back to like the grasping setup here, part of the reason that our like even more primitive imagery styling methods worked in this setting is because a lot of the actual like physics interactions are quite simple. All it needs to be able to correctly model is that like your robot is going down and it's like closing its grip around a single like rigid object and then it's lifting it out. And that's really the most complicated thing it needed to do. But as we try to do things that are more dexterous with robots, it turns out understanding the fine grained manipulation ends up becoming really important. Uh, so then things tied to like physics of objects acting incorrectly or like object permanence like being somewhat wrong or like other things like this all end up being like things that make it challenging to use like existing video models for robotic settings. This is in fact one of like the failure cases from the original Sora release where they discussed like the ways in which their current models are somewhat limited in this respect. Um, there's a lot of like ongoing research here. I've personally been like a little bit less in touch with how effective these models have been, but it's something where I think that like there could be some like progress there, assuming things work out. Oop, why is this not good? Okay. Uh, so then I think the other challenge that I want to discuss is this notion of usability of the robot. So when I think about ways in which people have used large language models right now, I think for me personally, like the sort of main use cases I use it for are either like doing like editing of like text I've written or doing it for like coding assistance. And even though like existing large language models will like do edits that I don't agree with, or they'll like write code that seems like incorrect to me, I still find it helpful because I'm using it in a task where like the errors are really easy for me to fix. I can just sort of like delete and backspace all of like the parts of the generation that I don't want. And like there's not really too many long-term consequences to this. Like because the errors are so easy to fix, then I can just like find the errors in like the generated code, remove that out, and then just like check in like the correct code after I get it through code review. And additionally, just like writing things is difficult and like writing code is difficult. And because these tasks are hard, I'm okay with like a partial solution that I have to like do a little bit of babysitting for, and this will still help make me more productive. Um, I think that then when it comes to this challenge of like, we would like to have like a robot that helps us around the house and like does our dishes and does our laundry and so on. All of these things that we want robots to do are things that we can also do. Like it's not hard to wash the dishes. It's not hard to do laundry. It's just that it's time consuming and we would like to spend less time doing it. Uh, and so I think that there's been a little bit of like a user experience or like human robot interaction style argument to this of like because the task is easier, the standards for what we consider a usable robot are higher and the tolerance for failure is lower. And sort of the example I like to give for this is that like say some researcher comes up to you and says that they've made a robot that will help you like load dishes like in and out of the dishwasher and it succeeds 97% of the time. So that's like a very high number. In fact, that might be higher than a lot of like example numbers I can think of from the literature for trying to get this out of like humanoids right now. But like I personally would not use a robot that dropped my dishes 3% of the time. I feel like if I did, I would very soon run out of dishes. Um, so because of this, robots need to practice. This was one of the more recent projects I worked on before I ended up switching into like AI safety and alignment. Uh, for robots to become more reliable and better at doing all sorts of tasks, then we need to put them in more diverse environments. We need to get them to try like more diverse tasks. We need to like understand what things current models are good at and not good at and slowly expand the space of things they're trying over time and make sure that we've set up our environment in a way such that we can do this. Um, to draw an analogy to like self-driving cars, which you could view as potentially a kind of robot, you can think of this as like you can either choose to like solve a narrow task now, or you can try to like do this like straight shot towards getting like an L5 autonomous like self-driving car, or in our case, getting like a robot that can like really do anything that a human can. I personally am more interested in trying to like get directly to this like L5 autonomy level. So this is a paper that I worked on back in around like 2023, so last year. It's called AutoRT, Embodied Foundation Models for Large-Scale Orchestration of Robotic Agents. And really, there was a lot going on in this paper, but the short version is that we were trying to explore what it would be like if we had robots continually and autonomously roaming around in an environment and practicing tasks as aided by some large language model. So what we did is we set up a bunch of environments all across Google Campus. We set out like a bunch of objects that they could potentially interact with. And we didn't prescribe anything that the robot in particular needed to do. Instead, what we did is we took an LLM and we said like, all right, here's the scene based on like the camera image, figure out what you are observing, find the objects in it. And you are like a helpful household robot. And what sort of tasks might you do in this environment if you needed to practice like trying out behaviors? So based on this, the large language model would generate a large list of tasks that the robot could do. And then we set up a system around it by which those suggestions could then get sent to the robot, and the robot would then like autonomously try to attempt that task, or it would optionally ask one of the human operators that was supervising it to provide a demonstration of how to do that task if it believed that it wouldn't be able to do it itself. So one of the benefits we found from doing this is that it really like leveraged the generality or the world knowledge that is existent within large language models so far, and made it like somewhat easier to like deploy them in newer novel environments because we didn't have to spend as much time prescribing like these are exactly the objects that are in the scene and exactly the kind of tasks we want you to practice. We also found that it made the robots like a little bit more steerable. So we had some experiments where we said like, you're a robot which is going to be used in a kitchen. What sort of like kitchen related tasks would you do? And you could like get the large language model to generate tasks that were more like related to food preparation, and then the robot would attempt those things. But once we introduced this more like automated task generation setup, then it also required us to spend some more time figuring out like the safety of the system. Like naively, it turned out that like some of the things the robots like to do is they like to practice like picking up knives, and this was not really a thing we were comfortable with at the time. So we ended up doing this thing where we did what we called like constitutional prompting, inspired by some of the work that Anthropic was doing at the time. And we would include these like automatic steps of filtering to make sure that like the tasks that were generated by the language model didn't violate like rules that we wanted the robot to follow. Like we wanted them to not pick up any sharp things. We didn't want them to like interact with any like living things. We like told them like, here is like the maximum amount of like payload that you can move. So you should like not try to move furniture that's heavier than this and so on. And we found that by doing this, we could improve the safety of the goals and tasks that the robot were attempting by around 3 times. And we were also able to have one human supervise multiple robots. So we went up to around like 1 human for like 5 robots, doing all this sort of diverse data collection. And by doing this, we were able to get both more relevant tasks for like robots to practice, and also like ease the amount of a human supervision that was needed in our data collection efforts. So I think I might be coming up towards like the end of the time I have allotted. So I want to like just do a little bit of like a wrap up thing here. So this was like an old like tweet from like Andrew Ng back when he was working a lot on speech recognition. And it's always stuck with me because basically understanding how to transcribe audio into text used to be very bad, and then it slowly got better and better and better. And then there was like some point around like 2016 where it actually became reliable enough that people used it for real. And this is like what I consider like the viability threshold. So I think Andrew Ng in one talk, he said that like 90% accurate speech recognition is not a product. It fails too often. People get annoyed by it. once you get to 95%, people actually start using it. And then like if it gets more accurate than that, then like we'll start using it more often from there. And I've thought about that a lot in the context of like robotics, where robotics right now haven't crossed this threshold yet. They haven't hit this point where they succeed often enough that they are solving more problems than they introduce. Uh, so I think that despite this, then there's still a lot of investment into space, because the idea is that once it crosses that threshold, once it gets to that point of like, oh, this is actually useful now, then there will be like a really big like market for them. So a lot of the excitement right now is driven by this belief that with the progress that is going on with like in AI right now, we can cross this threshold as long as we scale up and spend enough resources on like scaling up hardware, getting more data, getting better integration with LLMs, just future iterations of like foundation models, understanding the world better, and so on. And I think it's an open question on whether that will be the case, but it'll certainly be like pretty interesting to see if that ends up coming true. And I do think that now is like plausibly like the time when robotics might like finally like start working and become a more of like a household thing. So I think that despite all of this promise, or like all of the interesting things that are going on in robotics right now, I've recently like switched out of it to work on more like AI safety things and more alignment things. And part of the reason that I've done this is that like as I've been working in robotics over the past few years, I've observed like this progress from all of these like more like foundational large language models of like the jump from like GPT-3 to 3.5 to like 4 and so on. And one day I like sat down and just thought to myself, like, when human level autonomous agents arrive, where are they going to come up first? And the conclusion I came to is that because of all the friction of dealing with real hardware, it's very likely that they'll first arise in software only settings. Everybody I've talked to in robotics agrees with this. Hardware is just really annoying to deal with and creates a lot of drag on like the amount of research you can do. So I think that like I'm a little concerned about some of the harms that could exist if you have like human level like software only agents. I think this is still enough of like a capability threshold that they could do some like pretty crazy things. And this notion that like reality is like very complicated can like go both ways, where historically the biggest failures that have occurred in the course of our history is when like everybody assumes that something is safe, but it actually isn't safe. So this is one of the lessons that people like drew from like the 2008 like financial crisis, for example. Everybody thought that like housing mortgages were like an incredibly safe investment because people always pay off their mortgages. So then they leveraged themselves up on them incredibly large, and then eventually it all like blew up. Uh, I'm a little worried of like a similar thing potentially happening in with like AI systems in the future as they become more capable and as we delegate more responsibilities to them. I'm not sure if we will have like sufficient like supervision into what those agents are doing to guarantee that like they'll always take actions that are in line with what we would want these like human level autonomous agents to do. So this notion of how to like monitor like smart autonomous agents at scale and like understand what they're doing and make sure that the actions they're taking are good ones is, I feel like, pretty like unsolved right now. And the current methods for doing so, I'm not confident that they're going to like really like scale up as models become more capable. So that's sort of the stuff that I'm interested in these days. This idea of how do we make these like large language model driven agents be more reliable such that they could be more usable in like higher risk settings. All right. So yeah, that's it for the presentation. Thanks for listening, and I believe there's like a Q&A session after this, so feel free to send me any questions.
Just wondering, as the large language models get more powerful, can you apply them to help with the robot training? If so, will that accelerate the advancements of the AI robot integration to keep up with the LLM models?
It should, or large language models have been getting used in robotics so far, and that like I know people on the team have been trying things with them. Right now, the bottleneck is that a lot of what we care about in robotics is more of like a visual problem of like given this image of the scene, I want to be able to like reliably find where everything in it is and like understand how this is going to interact with this and so on. Uh, so I think that given a lot of, I think a lot of companies tend to focus on just making like the language reasoning side of it be better. So in order to make them be useful for robotics, then there needs to be more work into like the visual understanding side of large language models. But I know this is like an active area of like interest for people, and I think that as they become better, they could accelerate like parts of the robotics pipeline. I think the part that they're not accelerating right now, and which I don't see them accelerating in the near future, is this notion of like the low level like motor understanding of like how much should I be like torquing this motor in order to like move my arm correctly, because it's just not something that is really like very like legible in text at the moment.
There was one question that you said that even though simulation you were able to find data, but most of the time when you tried it in real world it failed. But were you able to find out that what went wrong, and then again went back to simulation to enhance that, to add that thing? Were you able to observe any results that were different from the previous one? Have you had done this?
So we did some tuning of the simulation, but we for that project we were a little deliberate in trying to not make the simulator like really match reality as strong as we could, because the goal of that project was to try to bridge the gap between simulation and reality with some like machine learning or like AI style method. Sort of the way we are envisioning using it was using it in newer settings where we would spend less time setting up a simulator for the exact task we cared about, because we would believe that our model would be able to fill in the gap for us. We did bridge some of the gap between the two, but it wasn't like a focus of that project, because like the goal was more to like examine methods to bridge the gap rather than achieve like good success on a single individual task.
While you were talking about the auto RT stuff, you made a passing comment that caught my attention for a different reason than you were making the comment. You said something like it had a tendency to want to practice picking up knives, in the absence of guiding it around that. I'm wondering, was there something in that system with the LLMs that would actually incentivize it to want to practice a skill
I think for that one, most of the incentives were just sort of like driven by things that we had in the prompt. Like we told it to try like picking up objects in the scene, and it's just the case that if one of the objects in the scene happens to a knife, then it would like do that some of the time. I think that when we looked at like the kinds of objects that it decided to do, it seemed to mostly be like uniformly random between like the different options that were like in view of the robot.
Okay.
We did discuss some potential follow-up things of like if we included like our empirical history of how successful the robot was at like certain like kinds of objects and included that in the prompt, would that affect the generation of like what things like the robot would propose trying to do? But we didn't really explore that in this project. That was like something we'd said as maybe we'll do this later.
You have a bunch of robots in a common room, all doing the same thing, with largely driven by a shared foundation model, presumably running on a server someplace accessible to them, right? In the real world, I'm going to have one of those robots in my kitchen, and you're going to have one in your kitchen. They may share a model for some things, but they need to be doing some learning locally. The embodied part of the robot, the embodied part of that intelligence is going to be in my kitchen or your kitchen. And so you need to have some learning component there and maybe a shared component. And have you done any exploration of how to break that into two parts so that I can have a robot that has the benefits of the shared large foundation model that you created and still is doing learning about my kitchen?
It's been a topic in the team. Well, I should say more accurately, it was a topic in the team when I was there, like around like 5 months ago or so. I think that we were calling it like data efficient, like fine tuning at the time, trying to see how few examples could we provide to a robot to have it start to learn how to take actions within like the new like novel like lab environment we had set up for it. So it's definitely something that people are thinking about. I think that because the base behavior of the robot like isn't like quite good enough yet, then I don't think there's been like a ton of effort into like per like environment like local fine tuning yet, because it's a sort of thing where like until like the base thing is good enough, it doesn't make sense to do.
It looks like most of your research is focused on humanoid robots, but I was wondering if other formats are being researched as well, like companions, like pet robots that could be companions for people.
Most of my research has actually been on things that aren't humanoids. So they've been on usually what we call like mobile manipulators. So like there's like a base with like 4 wheels that drives around and like an arm attached to that. There have been investigations into other sorts of forms. So I know that like quadruped like robots are like pretty like popular right now. I guess usually people call them like robot dogs or similar. I've seen like some ones of like toy robots where they just sort of like drive around on wheels, but then they cover them in a bunch of like carpet and fur and give them cute eyes. And all they really do is move around that blink at you and play cute sounds. But that's good enough if you want a toy. Part of the reason a lot of people are excited about humanoids in particular is that they believe that it's easier to solve the transfer learning problems, human video to like humanoid actions, if you use a humanoid form factor. Because like we know like humans can do everything in the world we've created, in theory a humanoid robot should also be able to do all those things. But I've also like seen some demonstrations of people doing like they made a humanoid robot, but it has 3 arms instead of 2, because they were like, why not have 3 arms? Maybe that would be useful in some way. Yeah, I think the notion of what form factor is the correct one is like quite open. And I think it's just the sense of like, you need to like really have a reason for like exploring this like more complicated form factor to like justify spending all the time building it. I think that's the main reason there's not been a lot of differences between the two, that there are sort of these base form factors which people have like found to be useful for like certain things, and they mostly just like pattern match off of that.
We're living in an ideal world. So what breakthroughs in research should happen that would enable autonomous, like full autonomous robots?
If it happened quickly, the way I see it happening is that the base foundation models got a better understanding of embodied visual reasoning, such that a lot of these like corner edge cases that we see are things that like language models just like correctly understand the things to do there. Probably there are better notions of like guaranteeing like safety of those robots, such that it's easier to get them to meet existing regulations around like what does a compliant robot like need to satisfy in order to like be around like everyday untrained people. And then like combined with those two things, I think that like the base cost of everything going down enough that you can actually like really scale up all these robots and get a bunch of data of like them handling all of these scenarios.
In terms of like autonomy, like what robots can do autonomously today? Like just to understand like where we are when we are talking about autonomy of robots.
In terms of autonomy, I think if you want to see them, the best places are to go to like manufacturing settings or like logistics centers. So I know that like Amazon has like used some like autonomous robots for a while, but it's mostly at the level of like they put a pallet of goods on top of like a moving platform, and the platform like autonomously like drives to the position it needs to be. Or you can think of it as like you maybe have like some like assembly like robot arm that is like at like in front of like a pipeline where like a conveyor belt is like bringing things, such that it'll like always be in a similar position. And I think that's where autonomy has like really worked, when you can constrain the environment down to like control out a lot of the potential like weirdness that could arise from a more like general like open world setting. When it comes to things that like are like really open world, I think that it's mostly just been like locomotion style things that have done okay. Stuff like driving like a Roomba like robot vacuum around. A lot of like the like quadruped dogs are like getting like really reliable at like walking around in just like unfamiliar terrain. But then once you start introducing like object manipulation, usually nothing's like that autonomous right now.